Hello everyone, Foxy here, and welcome to Mostly Mental. The Summer of Math Exposition is here once again, and this year, Grant has asked creators to make content for teachers in classrooms. And this is a math education channel, so it probably comes as no surprise that I have an interest in how math is taught. So I'll take this opportunity to share some thoughts with the teachers in the audience. If you ask a mathematician what math is all about, they'll describe it as something like exploration of the structure and patterns of the universe. But if you ask a student learning math, they'll probably say it's memorizing a whole bunch of formulas and equations. Where does that disconnect come from? Well, they're coming across the information in two totally different ways. The mathematician stumbles across an interesting pattern and then plays around with it to figure out what's going on. That involves a lot of messy calculation, guesswork, wrong turns, backtracking, and most importantly, building up intuition. But the student is handed a complete, polished answer, seemingly from on high. And there's no reason to develop intuition when you have the answer in front of you already. A lot of clever people have thought about this problem, and they've come up with some alternative models for math education. I've taken the best parts from some of these models and blended them together to create something I think would work even better. So today, I'd like to present this new model. It's all about building intuition through finding patterns, so I call it pattern discovery. In a traditional lecture-based model, most of the learning happens in the classroom. In a lecture, the teacher introduces topics, provides some context, and then explains the rules for working with the things they've just defined, how to add fractions or multiply polynomials or what have you. And then the homework and follow-up discussion are mostly there for practice and reinforcement. In broad strokes, pattern discovery takes this explain the rules step out of the lecture. Instead, the homework asks students to build up intuition through examples and to create those rules. And every step along the way is driven by finding patterns. That's all a bit abstract. It'll make much more sense if we go through a sample lesson. The first step in the process is to introduce the topic for the unit. This introduction should do two things. It should define the objects of study, and it should provide context. And a natural way to do both is through finding patterns. That means using multiple examples and guiding students to see the connection between them. For instance, let's introduce a unit on fractions. We might start by talking about something familiar and intuitive, like ordering pizza. If 4 friends split a pizza between them, they could cut it into 4 equal pieces so that each person gets 1 out of 4. But that's not how a pizza is usually cut. More often, you'll see it cut into 8 slices. And if we cut it that way, then each person will get 2 out of those 8 slices. No one's getting any more pizza this way, they're just splitting it up differently. But how can we have twice as many pieces and still have the same amount of pizza? Then we might move on to an example from sports, asking whether LeBron James or Steph Curry is the better shooter. After the students express their gut reactions, we can bring in some numbers to make a case. LeBron has made more than 15,000 shots out of more than 30,000 attempts. And Steph has made more than 8,000 out of more than 18,000. So LeBron has made a lot more shots, but he's also taken a lot more shots in total, because he's played for 6 seasons longer. How can we make this comparison on more equal footing? Or we might talk about ice cream. Say we have 3 friends and 2 tubs of ice cream, 1 vanilla and 1 chocolate. But one of the friends, the blue one in this case, doesn't like chocolate. Well, if they all split up the vanilla equally, then each of the friends will get 1 out of 3 portions of vanilla, and the 2 who want chocolate will each get 1 out of 2 portions of that. So, how much ice cream does each person get in total? Does that seem fair? If they rearranged to make it fair, how much vanilla would each person get? Once we've seen a bunch of examples, we can identify a common thread between them. In all of these cases, we have some number out of some other number, some part out of a whole. We'll write that as part over whole, and we'll call something written like this a fraction. The part is called the numerator, and the whole is called the denominator. These examples also suggest ways we might want to work with fractions. We can think about equivalence or comparison or addition and subtraction, and it's worth pointing that out to the students as a signpost for where the lesson is going. But remember, the goal here is to lead the students to discover ideas, not to spoon-feed them the answers. So it's important not to explain the methods in this lecture. Just give them enough context to justify spending time on the subject. This context makes for a good foundation, but with pattern discovery, most of the insights come from the homework exercises. So, what do these exercises look like? Continuing with our fraction theme, the first few questions ask students to count the pieces of some shapes and to find the fraction of each shape that is shaded. These are pretty simple questions, and they can be answered just by pattern matching with the given example, but they serve 2 purposes. First, they reinforce the definition of fraction covered in class, and second, these pictures look a lot alike, and within each of the other groups, the pictures will look a lot alike too. This hints at the broader pattern that we're searching for. The next group of questions asks the students to go the other direction, from fractions back to pictures. Again, these are relatively straightforward exercises to build fluency, but the example fractions are chosen deliberately to highlight a pattern in the numbers. And when we draw them, we again see pictures that look a lot alike. That suggests that this pattern in the numbers and the pattern we saw earlier in the pictures are really the same pattern, or at least related. Finally, we come to the questions driving the whole model. What pattern do you see, and why do you think this pattern is there? As I've said along the way, the pattern here is that some of the pictures look alike, and more specifically, if you have a fraction and you multiply numerator and denominator by 2 or by 3 or by any other number, you'll end up with pictures with the same area shaded. Why? Well, draw a picture for a fraction like so. Then take that picture and cut each of the pieces in 2. We now have twice as many pieces in total and twice as many shaded pieces. In other words, we've multiplied numerator by 2 and denominator by 2. And this same idea will work however many pieces we cut everything into. So we've stumbled across this idea of equivalent fractions just by counting things, drawing pictures, and searching for patterns. Of course, these exercises need to be followed up with good classroom discussion. The goal here is to make sure that everyone is on the same page and that the students all understand the intended patterns. This is the part the teachers in the audience are already trained to do. You know this much better than I do, so I won't try to prescribe a method here, but I will make a few suggestions. First, connect the pattern back to the context. For instance, one of the examples we used to motivate studying fractions was splitting up a pizza into either 4 or 8 slices. And we commented that it suggests a notion of equivalence. Now that the students are familiar with equivalent fractions, we can revisit that example, and we can see how the thing they've just learned applies to the problem that inspired it. Second, the students will come to class having already thought about the key ideas. So, this discussion gives them a great opportunity to practice technical communication. You might have students practice speaking, either in small groups or in front of the class. Or they might read and workshop each other's written descriptions of the patterns they've found. Anything that helps them improve at sharing ideas. Third, it's possible, even likely, that students will come up with patterns other than the ones that were intended. When they do, that's great. Reserve some class time after the initial discussion to explore those patterns and encourage that curiosity. The beauty of math lies in the unexpected connections. And finally, learning is an iterative process, so you'll need multiple lessons on any topic, ideally approaching the idea from different perspectives. Plus lots of practice and reinforcement to make sure the concepts really stick. You're likely already doing this, so keep at it. So we've seen pattern discovery as a model for building understanding through finding patterns. But why should a teacher use it? Well, this model is based on other proven approaches, like discovery learning, project-based learning, and the flipped classroom model. And there's been lots of research into what makes these other models work. I'll link some of that in the description below. Pattern discovery is designed to have some of these same strengths. For instance, the focus is on intuition, not memorization, in line with how mathematicians think about math. Intuition is much easier to retain than a formula memorized for a test, and it creates a strong foundation for building future concepts. There's also an emphasis on motivation. Every math teacher has been asked, when will we use this in real life? With this model, that answer is placed front and center. Pattern discovery is a form of active learning. That is, students engage with the material, they don't just passively listen. And active learning has been shown to help students understand and remember ideas better. Pattern discovery also helps smooth out pacing issues. Students don't pick up ideas at the same speed. In a lecture-based model, that means either waiting for the whole class to get each key point, boring the faster students, or moving on sooner and losing the slower students. But with pattern discovery, where the insights come from the homework, the students can work to their own paces. Finally, pattern discovery works as a drop-in replacement for traditional lecturing. That means you can get all of these other benefits without having to restructure your classroom or alter your schedule. And it works on a unit-by-unit basis, so you can just replace the lessons where students are struggling without having to replace any of the lessons that are already working for you. To be clear, I'm not suggesting that pattern discovery is the best possible model for math education, or that it'll work for every teacher in every circumstance. There's no shortage of people telling teachers how to do their jobs, and I'm not trying to be one of them. My goal here is to give you a tool, which you can use or ignore as you see fit. I just want to turn the patterns that got me into math into a way to engage future students. But now I'm curious to hear your thoughts. Would this model work for your classroom? Is there some feature of it that you like? Do you have any questions or suggestions for how to improve it? Please let me know. I'd love to hear from you. Thank you for watching. I hope to see you again soon.